Good morning. I'm showing 9 o'clock on my watch here, so we're going to go ahead and get started. My name is Mike DeLaCluse. I'm president of Lesman Instrument Company. I'd like to thank all of you for taking time out of your busy schedules to join us for Mechanical Flow Metering Solutions. Our presenter today is Bruce Patterson of Great Plains Industries, also known as GPI, and manufacturer of Flomec flow meters. Bruce is going to give you some insight into mechanical flow meter technologies and how some infer the flow rate and others, like positive displacement, know exactly how much is going through them. By the end of today's session, you'll know how to get coriolis type accuracies at a fraction of the cost. Bruce has worked for Great Plains Industries for more than 25 years, serving first as an OEM product manager and major account salesman, and now serving as the Western Regional Manager for GPI's industrial meter product line in the United States and Canada. He holds a bachelor's degree from Pittsburgh State University. We will be muting the phone lines. If you have any questions, there's a question tool built in to GoToWebinar. Please send me the questions and I'll get them answered. With that, I'll turn it over to Bruce.
Good morning. Welcome to the webinar. Today we're going to talk about measuring flow. We're fortunate in today's market that we have a choice of a wide range of materials and technologies so that almost any flow application can be handled accurately and reliably. Most of the technologies have their origins many years before any of us were around. Some of them, however, represent a more modern era. Meters range in complexity from a simple variable area meter to the multi-phase sonar meters used in offshore oil production that can actually tell you how much gas, oil, and water individually are coming through the line at any given time. As Mike indicated, some of these meters measure actual volume in a positive displacement fashion. Others look at variables that can be converted to whatever engineering unit we need, whether that requirement is for mass, volume, or rate. And almost every application will have a combination of those things. Here's one example. We kind of break these down into two different groups here, mechanical and electronic. And that's done by sensing type. Some of the more modern era meters use sophisticated electronics, sound, or magnetic principles to detect flow or velocity, and then they convert that in a computer to usable information. Included in this group would be the mag meters, the ultrasonic, thermal mass, and as I said, the coriolis meters. And as I said, we call these as a group electronic meters. Then we get to the next group, and this is the most common technology, and this utilizes a sensing device directly in the flow path. The technology with the largest installed base, believe it or not, is one of the simplest. It's a VA meter. It's very simple. It just consists of a float contained within a tapered tube. So the faster the flow, the higher the float rides in the tube, and you can read your flow rate off the graduations. As long as you can produce a linear representation of the variable, you can measure flow. So whether it's as in the VA meter, a marking on the side, or whether it's a frequency that we're generating, as long as it's linear to the flow, we're good to go. Some of the older technologies include turbines, oval gears, impellers, nutating discs, vortex shedding, even the differential pressure meters are in there. But they all have one thing in common, and that is they have some kind of device located within the flow path that either spins, turns, wobbles in some way to provide a representation of the variable with a linear relationship to flow. And these are mechanical meters, and that's kind of what we're here to talk about today. So meters in general have a very broad range of application. It'd be very rare for an application to only have a single meter or a single technology that would work. So any metering requirement, there will be multiple materials and multiple technology options. And here we're seeing material options. We show a metal-free PVDF meter at the top, specifically designed for acids, an aluminum meter on the right, and a stainless steel on the left. So about any kind of fluid that you get to, we can get to a material to match up to you. This isn't to say that any of the usable technologies will be the best to handle that application, though. Usually there will be some requirement or specification that points to a specific meter. Technology or the ability of the meter to measure the fluid is not always the key requirement either. There's also a lot of other things that may come into place. It may be a space restriction, budget constraints, accuracy requirements, or user sophistication. You know, I don't want to put a meter into a place where the user doesn't understand what it's doing. That just seems like a recipe for disaster. So we want to make sure that the user sophistication is considered in that. But all of these considerations add up to value, and that's really what we are trying to generate here is value either for our customer or if we are an end user for our company. Some of these are very simple, uncomplicated designs, and some more complicated. So we understand what the value equation is. Benefit minus cost equals value. So as we go through this, we need to look very closely at what is the benefit. What is the one best thing that will bring the best value to the customer? And one of the things I talked about a little bit before was accuracy, and this is always a big issue with people. But I want to go through a little bit the two important points in accuracy and how these get represented by the manufacturer. There are two ways that we can report accuracy and two things that affect it. Typically, it will be stated as a plus or minus X%, but the important factor in that is we have to know whether it is an X% of full scale or an X% of reading. And because there's a huge difference as we get on into varying flow rates. So here we have a chart that illustrates the difference in allowable error on 2 meters, both listed as a plus or minus 1% meter. So as we can see there, if you are a percent of reading, that 1% is going to go from the very end of the flow range to the top. So whether I'm doing 1 gallon a minute or 10 gallons a minute is irrelevant. I'm going to be within my 1% as stated by the manufacturer. I'm going to be within my 1% all the way across. However, if I've got a full scale meter, and an example of that might be the impeller meters, a little insertion meter, they'll typically go on full scale. And full scale is generally used where flow rate is the important factor, not the total. So we need to keep that in mind as well. And as we get down to the lower end of the flow rate there, a meter flowing at 1% meter flowing at 1 gallon a minute, even though that's might be in the stated range, is going to be nearly 10% off. So on a 10-gallon dispense, if we're going to go to totals, instead of having plus or minus 0.1% here, 9.9 to 10.1 like we would on the reading meter, we're going to have 9 to 11. So you've got, almost a full gallon of error there. The other thing is the absolute accuracy of the meter. And different applications require different things on this. So we can be accurate but not repeatable. And if I am monitoring a flow rate. I want to make sure that I've got about this kind of flow going through there. If I'm looking at something that I'm not really that concerned about, but I want to know, one example of that we get is people measuring runoff water for EPA. They want a pretty good general idea so they can report it. They're not that concerned. It's not a profit center, so you know, they'll take a plus or minus 2 or 3%, and they don't really care if it's repeatable either. So those meters, I know we have one that retails at $170. You can do pretty well with those in those types of applications. Repeatable but not accurate, that becomes a lot more application specific, and the application will define that. If I am blending a product and I know that when my meter says it's 10.3, my product is perfect. I don't care whether it's 10.3 or 10.8 or 11.2 in actual volume. What I really care about is that my blended product is coming out the same every time when this meter says 10.3. Then you have the other set here, accurate and reliable. And these meters tend to be quite a bit more expensive. It seems like price and accuracy go right along together. As I get into fractional percentage meters, they get a lot more expensive. The technologies get a lot more expensive. But that's going to give you not only the exact measure that you're looking for, but it's going to give you an accurate measure. And in something like that, one thing I think about there are pharmaceuticals, where I have a concentration of a certain drug that I'm wanting to have in this injectable solution, and it has to be the same every time. So all of these things go together to make up a solution. If we didn't have problems with flow, we wouldn't be here. So what constitutes a solution? Does it solve the problem? Is it going to give the customer the things that he needs? Is that solution deliverable? Can we get it? One of the things that happens a lot is we have this great solution, we go out and start looking for it, and yeah, we can get that, and it's 15 weeks later, or that's just in development, we can't quite get you there yet. But so having a deliverable solution and in the time frame that the customer needs is a big part of it. Does it fit the sophistication level of the user? Once again, you know, we have to take that into consideration. I'm going to you know, treat a mom and pop organization with no real technical ability differently than I will a large company with an instrumentation engineer who's speccing everything in. Does it stay within the budget? Boy, that's a big one. You know, the budget is key in a lot of cases, and it's not always expense, but again, we're going to get back to, does it provide the best value? People are always looking for the value. They'll spend $10,000 if they're going to get $100,000 out of it. They're not going to spend that money to monitor a flow line that really doesn't produce anything. So we always have to make sure that the budget and value make sense. So now that we've kind of gone through that, let's go through a little example. This is the Fairway Company, and this is all made up, by the way, so no lawsuits. They have an agent, and they inject this agent, and it modifies the viscosity of their pet shampoo. The fluid, it has a range of viscosities. When it's warm, it's fairly thin, it's 10 centipoise, but when it gets cold, it is 100 centipoise fluid. It is a conductive fluid, and it's typically, we're gonna be running this about 3 GPM. It's stored outside, so that centipoise does go up and down, but no real radical temperature. We're we're putting this in our line at about 75 psi. We don't really have any acid or base issues. It's a fairly neutral pH, and we're doing this with a piston pump, and we're using this meter as a verification that the stroke length we've got set on our piston and the frequency that we've got on our pump is correct. But it's in a real small pump room, and I don't have any way to create clear pipe run for it. All I'm looking for here is a total read, but I want it to be about 0.5% accurate. This really affects the viscosity of my fluid. That's one of my quality checks. I want shampoo to look like shampoo. I don't want it to look like grease, or I don't want it to look like water. So option one here, because it is important to our process, we could go to a coriolis meter, and that would certainly handle that issue. Very high level of technical expertise, however. I'm a small company. I really don't have an engineer here. I really don't want to go through all of that complicated setup and having to measure temperature and specific gravities and all those other things that go along with that. Additionally, this is a high cost option. You know, coriolis meters tend to get up there pretty high in cost, so that you know, I'm going to be spending several $1,000s. On the positive side, it's absolutely going to give me my accuracy, and it's absolutely going to be repeatable. I'm going to have everything that I need there. It's going to solve that part of the problem. But it's probably not the best value due to the high cost. And additionally, when we get into higher cost meters, they tend to load those up with everything in the world. So you know, I'm looking for a local total. I don't really need to have all of the outputs and all the different things that are going to be available and come with that. Option two is a mag meter. It'll handle the fluid, but it probably doesn't handle the pulsating flow very well, because this is an inferential type of meter, and it's going to look at velocity, and then it's going to change that velocity into a volume. And the other thing about mag meters, since they are looking at velocity, they require flow conditioning. I've got to have my pipe runs, or I've got to put in flow straighteners. I can't have a lot of swirls and spins and stuff going through my line and expect this mag meter to function properly. The mag meter gets me more into the cost that I needed to be at. It's a moderate instrument. You know, years ago they used to talk about mag meters at $1,000 an inch. I think that's probably only 30% of that now. They're coming down in price significantly, but it's still a moderate cost. Option three is the oval gear meter, and this is the mechanical meter. It actually has something in the flow path that's giving me a velocity. It is a low technology device. I don't have to worry too much about anything going on there. They're going to be a low cost device, and because of the cramped quarters that I'm in, and I don't have clear pipe runs, this meter, as a positive displacement meter, has no flow conditioning required. And additionally, it's going to respond very well to pulsating flow and changing viscosities. So this pretty much hits the nail on the head as far as being able to, number one, handle the application, and number two, meet my budgetary requirements. So the conclusion that we come to off of this, and I understand this was just one example, and since I made it up, I got to pick and choose kind of what I wanted to put in there. But there are all sorts of these applications out there. Many times when a mechanical meter is the best solution in providing the value that we're looking for, due to cost, due to simplicity, due to a lot of different things. So don't assume that the newer technology is better. These meters were all invented at some point to solve a problem, and the fact that they can solve many various problems is kind of an added extra plus. If everything was all the same, we wouldn't have all the different technologies and the different ways to measure fluid that we have now. And the last thing is never fail to ask the proper question. And I kind of threw that in there because if we hadn't delved a little bit into the specifics of the application, if a guy just called up and says, yeah, I need to measure this agent that's controlling my viscosity, and I'm pumping it into the line as an injection, we really wouldn't understand what the nuances of that application were. We wouldn't have understood budget requirements, we wouldn't have understood space restrictions, things like that. So I hope this has helped. I know this is kind of a short little session here, but the end result is that mechanical meters do offer a better result in a very, very high percentage of the applications. So when you're going out looking for things, your customer has a solution, or your customer has a problem that you're trying to come up with a solution for. Make sure that you're considering all of your options and not just going in and saying, oh yeah, here's a mag meter, here's an ultrasonic meter, here's something just because it's the new sexy technology. So that concludes my part of this. If anybody has any questions or comments, love to hear them.
If there are any questions, go ahead and type it into the question tool in GoToWebinar as we're concluding here. Bruce, thank you very much for your presentation. If anybody does have any specific application questions, please feel free to give us a call at 800-9-LESMAN or 800-953-7626. If you don't know your account manager, please feel free to ask for me, Mike DeLaCluse, and I'll make sure that you get taken care of. Our next webinar is going to be on Thursday, November 19th at 9 a.m. It's going to be presented by Herman Coelho of Siemens. Herman is going to talk about level technology for applications that are under 20 feet. Some of the more difficult ones are totes and barrels, and there's some new technology coming out to address those applications. Herman's a longtime product manager for this type of product. If you've never heard Herman speak, he's very knowledgeable on the topic and has seen just about every application out there, so you don't want to miss him. You can either sign up at the training center on lesman.com or wait for the announcement email to come shortly. There are some questions that have come in. Bruce, let me go ahead and read them off here for you, and let's see if we can get them answered. The first one is, what are the limitations on pressure and slippage past the mechanical flow meter?
Well, that's going to depend. I mean, we make meters that will run up to 10,000 psi. So it's an issue of getting a hold of the manufacturer, making sure that that they have an option for you there. So pressure limitations, they're really, I would say that would be it as far as I'm aware of. I'm sure there are some out there that can go even higher, because with a mechanical meter, you have to look at the whole picture. It's not just what the burst pressure is, and in most cases there is a pressure differential across that across the element. You're gonna have some pressure loss going across there. So that's going to be it, though. It's going to be around that 10,000 psi is the highest one that I've seen.
Can you address the slippage part of the question at all?
Yeah, slippage. I'm not real sure what he's talking about. I'm assuming he's going to be talking about bypass fluid. And again, that's going to depend a lot on the manufacturer. You know, on a mechanical meter, you can get low-end meters and you can get high-end meters. On our oval gear meters, if we have a stainless steel meter, the slippage is absolutely minimal. If for some reason those gears get locked up You've got a piece of gravel or something that comes in there and stops them from turning. They'll stop the flow just like a valve would. So there's absolutely no slippage there. If we're talking about a turbine meter, that's a whole different situation. The turbine can lock up, and you won't even recognize it downstream that there's a difference in your flow at all. So I hope that answered your question.
Yep, I think that does it. If not, we'll get an add-on. We are currently using coriolis meters, but as you mentioned, it provides all sorts of extra information. All we really care about is metering flow rate for a solvent lacquer-based paint. Flow rates are around 4 to 20 ounces per minute. Any issues with that application?
No. I think that you could, again, drop one of these oval gears in there, and one of the things with positive displacement, it lets you get to extremely low flows. I'd have to do a little bit of conversion, but the small oval gears can run down into like 1/10 of a gallon per hour. So I'm thinking that would probably get into your 4 ounces per minute fairly well. Now, the one thing that we would have to look on a lacquer or solvent type of stuff is, are we intrinsically safe? And so once again, that is an option. We could get you into a stainless steel that would probably handle or an aluminum. These are hydrocarbon-based fluids, so aluminum would probably work just as well. And then if you're just needing totals, we could easily put either a mechanical readout on it, or we could put an electronic display that would be intrinsically safe. So it really, yeah, we could handle that with an oval gear, and you would be at 20% of the cost of that coriolis, I would imagine.
All right, the next question, I'm not quite sure what the question is, but I'll read it to you. Are you going to describe mechanical meters and show some different types? I think we went through, variable. You went through. Okay, why don't you go back here? Sure.
Okay, so here is a group of mechanical meters. These all happen to be positive displacement meters, but at the top we see an oval gear, and basically that is two oval-shaped gears that set at 90 degrees from each other. When they turn, as we look at number 3, or the bottom of number 3 or the top of number 1, you will see that there is a small pocket formed between the flat side of the gear and the housing, and that is actually the measuring chamber. The volume that's contained in that chamber is known very, very accurately, and that's why we don't have much slippage, because you've got to have the length of that oval gear, and that measuring chamber has to be extremely precise, within 10,000ths of an inch. You basically get a capillary seal there, is all you get. So, but that then, as you can see, as they rotate, that chamber just switches sides. The nutating disc, kind of the same thing. That is also known as a wobble plate, but it spins, and this is the one on the bottom left of the slide there. As the fluid comes through, it makes that meter wobble, and it sets up again a known cavity for the fluid to fill up. Same thing on the oscillating piston. Let's see what else we have up here. Here we've got a vortex shedding meter. I included this in mechanical simply because it does have a bluff down in the flow path. As you can see there, it relies on a piezoelectric sensor to look at the swirls. And as we change that flow rate, the frequency of the vortices coming off of that bluff will change. And as it turns out, that is a linear equation. We talked about, we had to have something that was going to be linear in relationship to the flow rate. So the faster the rate, the faster my vortices come off, and I can sense those with that piezoelectric sensor. The pressure differential transmitter, again, it really doesn't have any moving parts, but it is mechanical in nature, so we included that here. Several different types of that, whether it's from just a restriction in the line of some kind, like a wedge meter, whether we have any kind of tapering in the line. That's going to give you something, again, that's linear to the flow rate. At the top here, the turbine meter. Turbines are obviously the ones that I am probably most familiar with, but they have a turbine, and this is an axial turbine. It lays in line with the flow path. As the flow comes through, the energy of that is used to spin the turbine. And generally there's going to be a magnetic pickup that's located outside of the flow path. But as we spin a piece of metal through a magnetic field, it's going to generate a pulse. And so that's what we can look for there. A lot of things come into play here. On this picture, you can kind of see there is some twist in the turbine blade. There's an angle on it as well. The way that those blades are addressing the flow path is amazing how much change you can get from them. On our G-series higher accuracy meters, they'll run those, they will come back out, bring them back out, pull the internals out. They will make corrections to that, and sometimes it's filing off the back edge, sometimes it's putting a little more twist in it, sometimes it's taking a little twist out, but we actually can tweak those then to where we get from 100 to 1,000 pulses per gallon across the 10 to 1 turn down range. So you can make that turbine do about whatever you want it to do. The variable area meter, again, we talked about that a little bit. Very simple in concept, a little more complicated in design because the size and shape of the float, the material of the float, all of those things are fairly complicated to figure out when you start designing one. But the fact that you get more bypass, the higher the flow rate, I get a little more bypass, and the weight of my float, or the gravity pushing down on my float, I can calibrate all that to a specific number along the sides there. So did that get everybody where they needed to get on mechanical meters?
Hey, you want to touch on paddle meters for a second? Do you have much
Yeah,
knowledge?
paddle meters, they're going to be very similar to this turbine, and some people call them a paddle wheel, some people call them a tangential turbine, and some people call them impellers, but they're all the same thing. And they are very good for constant flow rates. Typically, we'll see those in larger lines. You can get as sophisticated or not as you want. Some of the advantages of those are they can generally be hot tapped. So I don't have to shut my system down. I don't have to cut a chunk out of my pipe. I can hot tap it. I can drill a hole in it, and so my process doesn't have to stop. And some of the things that I don't like necessarily on the paddle wheels is I'm getting a very small sample of the flow profile. Whatever size that paddle is, that's the only place I'm sensing the flow profile. and they are a little bit sensitive about how deep I've got it into my flow path, whether I've got it exactly at 90 degrees to my flow path or not. If I've got it twisted a little bit, that changes the angle of attack of the fluid. So we have to be a little bit careful with those during our installation. But once you get them installed, if the installation is done properly and we've got our clear runs of pipe and our well-conditioned flow path, they're going to be as accurate as anything.
I don't have any further questions. Bruce, thank you very much again. If there are any questions that come through in the next couple of seconds, we're going to go ahead and conclude the webinar. Thank you all for attending out there. This will be recorded and put back out on our website. So if you want to watch it in the future or share it with fellow coworkers, you'll be able to do that.
Okay.
Again, Bruce, thank you very much. At this point, we will conclude our webinar.
Thank you, Mike.